You feel the road, glued to the terrain. It is here that mechanics disappears, and the car becomes a fluid movement of pure precision at the service of performance. Welcome to Ferrari Unpacked, the series that makes innovation simple. Episode 4, Suspension, the Invisible Dialogue. If the world were a gigantic, smooth ball without any roughness whatsoever, on which a car could drive at constant speed without changing direction, this episode's topic would not exist. In the real world, it has actually existed since the late Middle Ages, when someone had the idea of adding a leaf spring to a cart, creating the first rudimentary suspension system. That is, the system that helps us cope with the roads of the real world. Like the name implies, the suspension system suspends the vehicle body above the ground, positioned between it and the wheels, or the vehicle's so-called unsprung mass. Why? Well, think about riding a bike along an unmade road or trail. A bike without shock absorbers will let you feel every bump, dip, and unevenness of the terrain, transmitting it from the wheels into your body. Suspension was invented to provide comfort to vehicle passengers by decoupling what is under the wheels, the road, from what happens to the vehicle body. But it is also required to put the tires in the best possible condition to transfer forces to the ground and provide driving stability and control, otherwise known as handling. Everything in the suspension, like more generally in the design of a Ferrari, aims to find the best equilibrium between these two requirements: usability and control, or in technical terms, softer or harder suspension. Now that we know about the functionality of the suspension at a theoretical level, we can take a broad look at how it is made. Let's pretend that our tire is an inflated ball, and our arm is a mechanism which connects the wheel to the vehicle body. If our arm is stiff, the ball will be subjected to every irregularity of the terrain. What's more, in the event of voids, there is the risk of bouncing. If our arm is elastic, on the other hand, it would be able to damp the impact, absorbing the forces. As a consequence, the ball will be squashed less and will remain in contact with the ground, despite the irregularities. Now, what solid body is able to damp or absorb a force before then returning to its original state? The helical spring. Hooke's law tells us the elastic restoring force is directly proportional to the deformation and acts directly opposite to the external force which caused it. This is problematic in the case of a car, as it would mean that the car bounces with each irregularity. Thus, the shock absorber comes into play, a hydraulic brake which is able to damp the elastic restoring force of the spring. There are different types, but for now it is sufficient to understand the basic theory behind them. Imagine a cylinder full of oil, for example, with a mobile perforated piston inside it, able to slide. When the piston moves upwards, it initially leaves an empty chamber in front of it, compressing the oil in the rear chamber. The difference in pressure forces the oil to flow through the small ducts, filling the empty chamber. The movement of the piston is slowed by the effect of viscous friction, in other words, the resistance that a fluid exerts on a body moving inside it with a certain relative velocity. Think about walking into the sea. In episode 2, we explained that water is 800 times denser than air. As long as you walk slowly, you won't feel much resistance. But if you start running, increasing your speed, the water feels much heavier to move against. This is viscous friction. Back to our shock absorber, this means that if the force is exerted slowly, the oil will have time to flow and therefore the friction will be less. On the contrary, if the force is immediate, the friction will be greater. In our case, This means that the more sharply our spring releases the elastic force accumulated in the compression phase, the more efficient the shock absorber will be in neutralizing it. The contrary also applies, for example during gradual deceleration, when greater comfort is required. These two elements are enclosed within the structural portion. That is a collection of linkages with different geometries, which physically connects the wheel and chassis. Okay, so now on to practice. There are different ways to achieve a compromise between suspension, which is as soft as possible, in order to provide comfort, but on the other hand, particularly for a sports car, is also rigid in order to guarantee performance and control. One of the simplest is the anti-roll bar, which allows us to achieve suspension which is still soft, yet able to minimize roll. Another, significantly more advanced solution is the use of active suspension, a system capable of adapting its behavior to changing conditions. It can be divided into two main categories: true active suspension and adaptive or semi-active suspension. Let's start with the latter. The first Ferrari to offer semi-active suspension as an option was the F355 Berlinetta in 1995. And from then onwards, this system began to be always available as an option. It was an electronically controlled adaptive suspension system, which allowed optimum calibration to be obtained based on two different modes, comfort and sport. The electronic control unit set the calibration of the shock absorbers based on measured information, such as speed and acceleration, and the driving mode selected by the driver. The turning point was 2006, when magnetorheological shock absorbers were installed for the first time on the Ferrari 599 GTB Fiorano. So, what are they? The fluid inside the cylinder contains ferrous particles, which, if a magnetic field created by coils is applied, change the viscosity of the fluid in just milliseconds. When the fluid is denser, the piston is slower to move, and therefore damps the spring more. When the fluid is less dense, the piston moves faster, and therefore the shock absorber damps the spring less. This allows the driver to very easily adapt the behavior of the suspension according to their requirements using the magnetino dial, introduced just 2 years prior. But we'll talk about this huge innovation in another episode. Now we'll move on to active suspension. In this case, an electric motor is added, which is directly connected to the shock absorber with a traditional spring, a Ferrari exclusive solution that can almost instantaneously apply an opposing force to that from the suspension lever arm when stressed. In other words, it is possible to expand or compress the spring not just in relation to what occurs on the road, but on command. Let's say the vehicle hits a pothole. The wheel would naturally tend to sink into it, leading to a bump. With active suspension, a force is applied in real time, which counterbalances this sinking in order to make the lever arm go where it needs to, but without repercussions on the vehicle body. It is the ultimate way to achieve both usability and sports performance, each when required. We are clearly talking about FAST, Ferrari Active Suspension Technology, in which mechanics and above all software come together to create a highly refined vehicle management and control system. As of today, this type of suspension is installed on two very different models, the F80 and the Ferrari Puro Sangue. It is precisely this difference which helps us better understand its potential. The Ferrari Puro Sangue has a center of gravity higher than typical sports cars, and therefore has to guarantee a certain level of comfort in the passenger compartment. As a consequence, the suspension must be softer versus other Ferrari sports cars, which with a normal suspension system would lead to problems such as pitch and roll. The active suspension system eliminates these dynamics, however. The 48V electric motors can increase or reduce the height of the shock absorber piston rod every 0.05 seconds, with a force of over 5 kilonewtons. This choice is implemented by measuring the wheel dynamics 200 times per second. Thanks to this system, the Puro Sangue is able to offset load transfers and body movement, almost entirely cancelling out all lateral roll and moving the load onto the tires. The F80 is currently the Ferrari supercar with the highest aerodynamic efficiency, as we talked about in episode 2. It has a vehicle architecture which allows it to be very rigid and stick to the ground with incredible downforce. So in this case, the active suspension is not needed so much to offset pitch and roll, as to help the flat underbody to remain in ideal conditions at all times, avoiding sudden losses of aerodynamic load. In this supercar, the FAST suspension is supported by a double wishbone layout, typical for Ferrari, created entirely in Maranello using generative design technology. This is a procedure which allows the creation of the most efficient form for a given component. Using metal 3D printing, it is indeed possible to place material only where it is required, observing where the load stresses and force lines pass through. In addition to providing a perfectly optimized part, this offers the major benefit of lighter weight, because only the material which is required is used. The architectural freedom offered by the Ferrari Luce electric powertrain has opened up the road to important advancements in the fast active suspension. The 4-motor electric powertrain configuration, combined with 4-wheel steering, makes this vehicle the first Ferrari to have active actuators able to control vertical, longitudinal, and lateral forces in all dynamic conditions in all the corners. A Ferrari is the result of a harmonious set of components which contribute to achieving the best possible balance, creating a happy union between different driving needs and desires. Ferraris are pioneers of cutting-edge technologies and solutions, thanks to the technological expertise developed over more than 90 years in the world of racing.